Okay, guys, I wanted to be sure you're being able to record what we did yesterday with these periodic trend notes. And I wanted to be able to finish up the notes that we covered yesterday. The atomic size and of these first two slides, I have it on my file right here, and then we have another slide on ionization energy. We did cover several of these yesterday, but I wanted to give you a minute in order to record what was important, or if you had a chance to record. This is on size trends. This first one and the second one was a different visuals on how to see how the size of the atoms go from large metals to smaller non-metals. So let me go back here and give you a minute if you need to still record thing on the very first slide on that first page, and just noticing that they're largest on the to the left and down, to the left and down, and then they are smallest over here on the right. And this is due to having more nuclear attraction on the right-hand side. Okay, next we're going to see a larger view of the same trend, noticing that there's smaller over here, smaller nonmetals compared to larger metals. These are really larger metals. And because of that, it really plays a role in the trends with ionization energy. Okay, so here in my next slide, noticing between these two that these larger metals down here, if you go to the next slide on that page, have very small ionization energy, which makes them easier to lose. This is your third slide on the first page. So get a chance to write this out. The ionization energy is increasing as you go over to the right, which is the opposite of size. And because they have really high ionization energy, it's going to make it really harder to lose. Non-metals tend to have a hard time to lose due to this high ionization energy. Okay, so if we go on to your periodic table on the next page, the next sheet of paper, you could be able to record these notes to emphasize the non-metals from the metals. Okay, but the dividing wall between the two is this blue line right here, borons right here, and then we have silicon and germanium and some other ones. These green labeled elements are metalloids. So please make sure you've labeled them. Metalloids are going to behave a little bit more like a non-metal whenever they do bond. I will use a few of them throughout this next unit that we're doing on bonding. But non-metals are going to gain electrons or even share to make covalent bonds, but that's due to their high number of valence electrons. They want to get up to the 8. And they have high electronegativity. That's that desire for more electrons when they bond. That's what that is, electronegativity. And they also have a high ionization energy because they are not wanting, they're not wanting to lose. They have really high energy. So these two trends go together. They increase and go over to the right, which is opposite of the size trend. They go over to the left and down. So the nonmetals have higher electronegativity, higher ionization energy. They don't want to lose. It's harder to lose. But the metals that want to lose electrons, they have lower valence number. They're bigger in size. They're easier to lose. And they have high ionization energy and, they have low ionization energy and low electronegativity. So I hope you're able to get these written down on your periodic table. We're going to use this a lot and getting into charges of ions very shortly with this chart as well. So let's move on. We're going to look really into electronegativity. We have this basic picture of the trends, very similar to your other paper, but it has really low electronegativity for these metals, and then it gets higher for the metalloids that are the pink. You don't really see the pink. You guys don't have it colored. And then these tall ones are all the nonmetals, fluorine and so forth. But notice this right here on the side has a very low to zero value. That's the noble gases. Okay, the noble gases do not want to bond. They want to just be stable, having 8. Okay, so what's going on with that group 18, okay, is that I want to point out that fluorine, first of all, has a very high electronegativity, okay, but the noble gases have no desire for electrons due to having a full level. They have a high ionization energy, but have a 0 electronegativity, okay? So fluorine is the highest electronegative. You have to remember that noble gases have no electronegativity. Okay, the trend for ionization energy is that they're high in that column, but it's 0. It's 0 for the electronegativity. Okay, I have a video to show on this, so let's watch that for, it's about 30 seconds. So I'm going to put that on right now, and we'll watch that video here now. Maybe I can make it larger. Let's see if I can do that, and we'll turn that on here. Okay, so let's watch this.
Electronegativity is the ability of an atom to attract towards itself the electrons of a chemical bond. This property, indicated by the relative height of the elements, is directly related to the electron affinity and ionization energy of an element. In general, electronegativity increases from left to right across the periodic table, consistent with the decreasing metallic character of the element. Within each group, electronegativity decreases with increasing atomic number. The most electronegative elements, the halogens, oxygen, nitrogen, and sulfur, are therefore found in the upper right-hand corner of the periodic table.
And just notice that the 0 for noble gases is right there. Okay, and that is causing it to not want to bond at all, having high ionization energy and having 0 electronegativity. Okay, so let's go on to looking at ionic radius. I did not get to, actually, we're going to do one little more about electronegativity on the next page. This is all the values, numeric values. We're going to use this as a reference throughout the year, but we have a major dividing amount when we do this electronegativity difference. We're going to subtract the numbers of the differences between a metal and a non-metal when they bond, or a difference between tin and fluorine, or the differences between sulfur and oxygen when you make a covalent bond, or the differences between iodine and carbon when you make a bond between them. And so this difference is subtracting the numbers. If it's less than 1.7, it's going to be ionic. And if it's greater than 1.7, it's ionic, a really, really big difference in electronegativity. But if it's between 0.4 and 1.7, or even down to 0, it's going to be covalent. And we'll talk more about the polar and nonpolar parts later. But this difference we're going to be really highlighting a lot throughout the year, especially right now with bonding. So this paper will be more of a reference sheet, and we'll have it available, when we get to that point, looking at the difference between electronegativity to determine if it's ionic or covalent bonding. Let's go on to this next page, and I have it labeled here with the sodium being a metal representative and chlorine being a non-metal representative. And just notice here, my yellow covering of sodium is its size, but when it loses an electron to chlorine, then the electron leaves and then it makes sodium smaller. Its positive ion is going to be smaller. So positive ions are called cations, and they're normally less than in size than neutral atoms. And then when a chlorine takes on the ion, we're going to call it chloride eventually when we get to naming, but the size of the atom is going to be bigger. Notice this is a 182, but with the negative electron, it's going to be 334. So anions is the name for negative ions. They're going to usually be larger than neutral atoms. Okay, they're going to usually be larger in size than neutral atoms. Okay, and we just wanted to highlight what the metals on the left-hand side, sodium as an example, compared to non-metals like chlorine on the right, that generally cations are smaller than neutrals, and anions are generally bigger than their neutrals. Some of those questions may be a part of homework number 66. Okay, let's look at the last page on your notes. And here it shows the difference in size, how positive ions are getting smaller and negative ions are getting bigger. Just make note of that. We'll go into more examples later. But in this last page, it's going to help you with doing 19 on the neutral atoms. These are all neutral, but when they become ions and during ionic bonding, all the positives are going to be smaller. And even having a high positive charge like 10 being positive 4 is even smaller. And then when you have negative ions, you can put this line between them, like nitrogen, oxygen, fluorine are going to be more commonly negative ions. And noticing the more negative you get, and the new nitrogen ion is much bigger than the -1 in fluorine. So notice that the more negative you get, the bigger the ion's going to be. And the more positive you get, actually the smaller you get in size. We'll really talk more about this, when we apply it more to our homework, or you're going to be answering some questions today on 66 and 21 and 23, but we'll reinforce this Thursday and Friday to make sure you'll understand it. But we have a basic trend. This ionic trend is still similar to the size of atomic trends. Basically, it's small right here on the right-hand side, and it gets bigger and bigger to the left and down. But you want to compare the positive ions separately from the negative ions. Negative ions, notice that the nitrogen negative is much bigger than the positive of carbon. So you want to only compare negatives, and then you can compare them positives as well. Okay, but this is going to help you on those 3 homeworks. Okay, I'll make another short video maybe on 66 and 21 and 23 and put that on Schoology if you need the additional help today. Okay.